All right, so yeah, as usual, we can discuss the homework first, and if we have time, we can talk about other questions. See, question 1. Because it had 2 parts. First part was I guess it was like a true or false kind of question. The first was asking, is it true that the expected number of times an optimal arm is pulled for a learning algorithm of a bandit doesn't necessarily converge to 1? And then second part was if the probability of putting an optimal arm necessarily converges to 1. And I was thinking maybe Jean-Marie, if you're open, you could walk us through your solution.
Sure. So I started by defining T index A of n as a number of time our agent takes action A in the steps from 0 to n minus 1.
Nice. So something like summing up the indicator function that the action at time t is equal to this A from 0 to 1.
And basically, the idea behind that is that we need to prove. Well, maybe now I'm not saying what should be written, but just like the intuition behind it, that we need to prove that the number of times we use the optimal action has density going to 1. And so what I'm doing is I'm looking at the number of time other actions are taken, non-optimal actions are taken. And I want to show that you incur loss when you use the other actions. And in this way, I will be able to prove that those other actions should be used with density 0 when t becomes large. And yes, then I write a very standard formula for bandits, I guess, that we already used in the course, which is that the expectation of the reward for some time is the sum for the different action of the probability of taking this action at this time multiplied by the expected utility of this action or of the reaction to this action.
So it would be like TA up to time t times mu a, something like this.
Yes, so you directly took 2 steps where I took them separately, but basically the idea is that you can do this for each small t separately, and then you can sum over all the t and you get the formula that you wrote.
Do this each for each small t, like.
Yes, and actually with the definition of the course of ut, we need to multiply by well, okay, now you wrote it with a small t, so it's perfect. And I mean, it's a symbol we hadn't introduced, I guess. But that's fine. And then you can sum over all small t, and and you get what you wrote before with a large T, and
I see. You're saying it just
yes,
a reward at time t.
yes, exactly. So you can do
I see.
the reward at a specific interaction, and then you can sum it over all the possible time steps. And
I guess you're saying the expected reward at little t is equal to the sum of
exactly,
the
exactly.
indicator of at equals a 10
Yes, yes, exactly.
and from there we can get this.
Yes. So with the definition of UT that we have, I actually also did it wrong first, is that actually you have a factor big T in front, because UT is defined as the average utility.
Right. Or I could put one over t here.
Are we missing an expectation in the reward one?
I think mu is already the expectation,
Okay, but what
if
does
I'm
the
not
indicator
mistaken.
function mean?
Yeah, it is.
Yeah, there might be. Yeah, it's probably a kind of adder expector, right?
Oh,
Yeah.
yes. So to be precise, I wrote the probability of AT equal T and not the
Yes.
indicator function. Yes.
That's probably different. Which is the probability is the expectation of the indicator.
Exactly.
Yeah.
Yes. And yes, so we already got this. And then you can write the regret from those expectation of TA by basically writing that the regret for big T of pi and eta is equal to 1 over t, the sum for all action of the number of the expected number of time you take this action multiplied by the delta for this action. So delta is like the non-optimality gap of the action.
T7. Yeah, I guess I was calling this like C sub A, I think, in class, just to not have two T's being confusing. But times,
Yes, exactly. You were
yeah.
calling this C of A.
Yeah, I was just
Yes.
calling. Actually, originally I was also calling it T of A, but then it looked weird to write T sub A square brackets capital T. Changed it to C.
And then already by inspection, if you look at this formula, and you know that the regret will go to 0, then basically the expectation for the A's that have a non-zero gap will need to go to 0.
Yeah, I guess I just wanted to say that this equation is actually like, it's a pretty central equation. And I think it's sometimes it's called the bandit equation or the regret. It's called bandit regret decomposition.
Yes. And then you can conclude, because for all the non-optimal action, it's going to 0. For the rest, it must go to 1. Well, the density must go to 1, not the number, but yes.
Right. So I guess the
It's also for the expectation above. It should be the 1 over t times the expectation, not the expectation, probably.
so we have that the sum of the counts for all arms.
Yeah, the sum of the densities must go to 1. Well, must be 1.
It's equal
It's
to 1.
constant to 1, and
Yeah.
and since the other are going to 0, for the optimal arms, it must go to 1.
Right. So if you put this together with okay, this is just true. If you put these two together, then you get that sum for sum over A optimal is also let's do 1. It's okay, yeah, that looks pretty convincing. Does anyone have any questions on this?
Yeah, so I get this part, but why did we need the previous part to do this?
Like, I guess this part was just we basically derived this bandit trigger decomposition.
Oh, okay.
Which I don't remember if I think maybe we didn't write this down explicitly as a thing in class. We probably used it implicitly.
Yes, I remember.
But,
I think we used it, but we didn't derive it. And maybe
yeah.
at the time when I wrote the homework, it wasn't even used before. I'm not sure.
Yeah, yeah, but I think it's good to write it out separately because it is a important observation. Any other question? Yeah, so maybe we can go through second part.
Shall I do it too, or do you? We want to
Yeah,
change
sure.
the pattern? That's fine.
If you don't mind.
So I provide a counterexample, and I take a very simple bandit, which has just 2 actions, and the action 0 has a constant reward of 0, and the action 1 has a constant reward of 1.
I guess I read it like a delta distribution of 0 and theta 1 is the delta distribution of 1.
Yes. And for the policy, again, it's quite simple. I take like a very unnatural but simple policy where I choose 1 except on a subset which goes to 0, a subset whose density goes to 0. So for example, I choose 1 for every non-square numbers. When t is a non-square number. Yeah, when the step is a non-square number.
Right, so it's
Yes, and because it's a deterministic policy, we see that the probabilities are 0, 1, 1, and they are infinitely many times 0 and infinitely many times 1, so the limit cannot exist. On the other hand, because the density of the 0 is getting lower, then we are progressively using one with a density going to 1, and so we are learning the bandit.
Right, so I guess the regret up to time t of pi with respect to I guess we have to. Yes, I would just. We only have like one bandit in the hypothesis class, right?
Yes.
Should have said like eta a of 0 and eta a of 1. I think that was the notation we used before. And then so here, pick this eta. So the average regret is like I guess on the kind of order
1 minus square root of,
over,
yeah.
1 over square root of t.
Yes, exactly.
So that goes to 0 as t goes to infinity. Right. So yeah, this is a nice example, and I think a lot of people came up with something similar, either with square numbers or with the powers of 2. So I guess as long as we're allowed to make mistakes, infinitely many times, but we do, as long as the kind of density, the frequency with which we make the mistakes goes to 0, it can still be learning. And in fact, I guess that's sort of an important aspect of learnability too, because, for example, if we consider the epsilon greedy algorithm, where the epsilon goes to 0 as time goes to infinity, like that one ends up learning because it explores each arm infinite many times in the long run. But that also means that it kind of picks a suboptimal arm infinitely many times, but with lower and lower frequency. So kind of this property that we can make mistakes into into the future is actually also important for learning, because we if we commit it too early after like any finite amount of time, there's always some probability that we committed to the wrong thing. So in general, it will be important to, at least for like an anytime algorithm, it will be important to keep exploring from time to time to make sure we're not committed to the wrong arm. Any questions about this?
Interestingly, all of the learning algorithms that we've discussed, I believe, actually do have the second limit does actually go to 0, if I'm not mistaken. Because like explore then commit, for example. Is that true? Maybe no, maybe that's not true. Maybe the probability of a mistake in terms of this, like this number 2 item for explore then commit, does that actually? I don't think that does go to 0. It just stays.
Well, if you take the version which was the question 3 in this version, where you take export and commit and turn it into an anytime algorithm, we run it for like time horizon 1 and then 2 and then 4 and so on. So that one, arbitrary far in the future, is going to have some new explore phase. So it actually does have a probability 1 of choosing the suboptimal arm at during each of those explore phases. Just phases are short relative to the exploitation phase that comes afterwards.
Yep. Makes sense.
So my question is, I mean, it's a vague question, but like, would there be like situations in which we would, in some sense, want the probability of like taking a suboptimal action go to 0, in addition to knowing that we are learning the environment or the environment class? Like does it give us, does it imply something else nice?
Yeah, that's a good question. And I don't think I haven't encountered such a situation, but I can imagine that being a useful property to have. So yeah, it could be interesting to think of a kind of quasi practical scenario where that would be important. Yeah, because I could see that being an additional property that we do want.
I mean, the thing, my mind goes to some possibility where, like, there are some actions that are like have like high expected utility, but there's like some possibility of like that it will basically kill you, and
Right.
yeah, in something like that, and yeah, you're learning the policy, but like there's a chance that you are going to, like, I don't know, St. Petersburg yourself to something, or yeah.
Yeah, right. Like there's like leftover options to explore, but they're also like very high risk in a sense. And then maybe yeah. You want to make sure that they're also getting pretty unlikely to be explored. Yeah, I think that's I think that's a reasonable criterion to add. I mean, it's yeah. I feel like it's somewhat at odds with this kind of utility or reward-based learning, because if they do have, like, even though they're high risk, they have high expected value, then probably if we never explore them, then we miss out on potential rewards, so we're accumulating regret. But yeah.
Maybe if we have some upper bounds on the expectation of arms, then this becomes more likely, because you might be pretty sure that your arm is near optimal at some point.
Yeah, I mean, it's definitely something that could, in principle, just be included in a learning algorithm to be like, okay, you don't have to actually have the regret go to 0, just have it be like small enough, and that's good enough. Sort of like instead of optimizing, like kind of a satisfying sort of thing.
Also, maybe if your environment is changing or something like this, then you want to keep exploring.
Right. That is true. Yeah, I think these are interesting questions. Yeah, definitely. I could see it being interesting to explore. But yeah, for now, we can maybe move on to the next question. I guess the next question was a coding question. So we're probably not gonna work through it in detail, but I was thinking maybe if Koshin, you could walk us through your code just to like talk through like what it's doing and what the graphs look like that you got at the end.
Sure.
I can let you present your Colab maybe if it's helpful.
Yeah, happy to.
Yes, a question to, I guess I thought it would just be nice to see that you can actually run these kinds of things on the computer. And then the idea was to take something that's not a learning algorithm and take something that is a learning algorithm and see how they compare.
Mm.
Um,
Do you all see the Colab here?
yeah, could you make it maybe zoom in a little bit?
Yes.
Yeah, that looks good.
So I changed the code in the Bernoulli Bandit class just a little bit. But I won't go through that. So this is follow the leader. Basically pulling each arm once. And then this np.argmax thing is just a nice way of pulling out at each time the best arm so far. And then explore, then commit. This is the calculation of this parameter m, these first two lines. And so then all of this stuff with maxes and floors, casting to integers, and then the warm-up time period is that parameter m times the number of means. So then we basically pull arms in sequence for this calculated warm-up period, as you all know. And then this same expression gets the empirical best arm, and then you just pull that arm for the remaining number of times. And so then, you know, one thing I've always found in Python is it's very dangerous to have any global variables. It's very easy to accidentally use global variables inside functions unexpectedly. So I put this thing like just into a function, so there's nothing kind of hanging around. And you can do this thing with list comprehensions. I don't know how familiar everyone is with Python, but you can just run the desired number of trials in this way. And then, so then you run it, and then I put the plotting stuff into a separate block just so that I could rerun it without having to rerun all of the trials that take a while. And then the graph comes out looking like this. So we have a pretty clear thing going on. Follow the leader is clearly not learning. This blue line is follow the leader. And then explore, then commit, you get this nice square root shaped function. And then I had some stuff at the end doing, there's this line profiler in Python, which I won't go through a lot, but you can basically run this expression on the right here, says what to actually do, like run the experiment. This actually calls the function run experiment. And then this function here says I want to know which lines in this particular function took how much time. So it's just a very convenient way in a Colab to do some profiling. Install this thing. I should have run this. This is all IPython magic stuff with these % commands. For this particular thing,
Just a question with the chart. Is that showing the total error, or is I would expect it to regret to go down with larger times?
Yeah, so this is total reward, not average. I actually called the function the wrong name. As Felix pointed out, it's actually showing the total reward, not the average one. So
The total
That's why
reward.
the total regrets rate.
Yeah.
So that's why one of them is kind of a linear, close to
Yep.
linear function, and the other is sort of a square root of t. And then for
Yep.
average regret, you would divide this by t, and then one would stay sort of constant, and the other go to
Sounds
0 as 1 over square root of t.
Yeah, just when you're eyeballing these functions, it's nice to have it in this form, I guess. Anyway, finally, then you can run this thing like this. And you get over here just this nice kind of version of a profiler, because profilers usually are pain to use, but this is the function itself, and you can see, it's the binomial function that's taking about 50% of the time. So that's it. That's it.
That's Thank you. Any questions about this exercise? I guess maybe one thing to point out is just follow the leader was not exactly the same as it's like similar to taking just one round of expiration in export and commit, but it's actually a little bit different because as it was defined, it was taking into account the average of all of the pulls of the arm so far, not just first the initial one pull of each arm. Which I guess is something we could do in export and commit too, that we keep updating the averages after the initial expiration, but it's just much easier to analyze the algorithm if you don't do that. I guess for upper confidence bounds, for example, for UCB, we do update the means and the confidence bounds after each step, so that one is sort of more dynamic in that way. Should we move on to question 3? So question 3, I guess the idea was to see how to turn a non-anytime algorithm into an anytime algorithm, which was I guess something that I think came up as a question in one of the lectures as well. Yeah, and I was thinking maybe is Ohad here?
Yeah, do you want me to introduce this?
Yes.
Okay, so yeah, this exercise asks us to bound the total regret, given this compound policy, which I'll call pi tilde. Yeah, so
I guess
basically
maybe
we
can write down the assumption quickly.
Okay.
So we're assuming we have a family of policies pi t, which had a regret bound, and this is for the total regret, which I called red hat. So let's say we showed a regret bound, something like ft of eta. So as an example, we can think of export and commit, which we defined it for, we found an optimal m for each time t, and then we had a certain bound, which we're just calling FT here for that one. Okay, and then so in part A we constructed this pi tilde, which basically I guess runs. Maybe I should say. So we fix a series of lengths. T1. So these are the amount of time we run each iteration, and we define pi tilde as on a high level runs it's pi t1 for t1 time steps, and pi t2 for t2. And so on, and basically just each of these start with a blank slate of kind of erasing the history before. Okay, so that's the setup, and
then yeah, and under this notation, I is the number of blank states that we have to do. So I puts a strict bound. It's the smallest I, such that t is less than or equal to t1 plus to t2 up to ti. And this is also denoted as a t bar of I plus 1.
is the I guess the minimum such t or minimum such I.
Yeah. And to make the calculation a little bit easier, here we were supposed to split the regret into t different parts and into I different parts. And the first I minus 1 parts have a complete stage of running the algorithm PJ, while the last stage might have a tail that we might not execute the entire TI steps. But here I claim that since the total regret is monotonic in T, at every new step we only we can regret on a positive amount. Then I simply bound the regret by the algorithm that does all I stages completely.
Right, so we can bound the total regret by I guess going all the way up to j equals 1 to I.
Yeah, and this inequality that does require some justification. I wrote the total regret explicitly by writing it as the sum of the suboptimality of the chosen xn, and then split it into I subsums. But then at each subsum, the claim is that it starts with fresh knowledge. So the way it distributes is exactly like if we started the pi j on an empty state, and then that subsum exactly turns out to be this regret, the j term of the regret. And yeah, I think by the definitions of the exercise, this inequality basically shows all of part 1, because by definition we have a bound on its regret using f pj. Yeah, and for the next part, we just have to substitute in specific functions. Here we know that ft is less than or equal to square root of t.
Right, which is is the kind of situation we had for export and commit, for example, where we had a square root like bound.
Yeah, and here we sample the algorithms that had powers of 2. So so tk equals 2 to the k minus 1. Okay, so here if we substitute the sum, this becomes the sum of j from 1 to I of the square root of tk, which is 2 to the power of k minus 1 over 2. And we want to show that sorry, the exponent has j. Okay, yeah. So we wish to show that this is bounded by t to the minus 1/2 by a constant factor. We use the fact that it's a geometric sum, so I bound this by a constant times 2 to the I over 2. Which makes sense because this is basically the size of the largest element, and the rest are negligible. But to calculate I, this is defined by the largest j, such that the sum from 1 to 2 to the j is less than t. So basically, I is log 2 of t. Yeah, so yeah, it's the minimal, so that the sum is greater than or equal to t. Yeah, and if we substitute this expression of I, we get the square root of t exactly, and we can make it implicit by solving of the one by one off by one problems. And then that's basically it.
Yeah, so these are kind of approximate, but yeah, we could make it more precise. And can you say what sort of bound we get for the constant?
Yeah, so here I got explicitly c equals to say 4.83, and so we can bound c by 5.
Yeah, so yeah, basically yeah, there's some rounding errors here, but then accounting for all of that, we get another kind of square root of t bound with a factor of 5. Right, so we see that yeah, this is we do get an anytime algorithm this way with a slightly worse, but kind of same asymptotically same like up to a constant same bound as the non-anytime version. Yeah, thank you for
No
walking
problem.
us through that kind of thing. Any questions about this problem? Yeah, I think most people who try to do this question got the right idea. I guess the first part was like fairly straightforward, except that if you wanted to be precise about like proving all of these, I think it required a bit of care. And then the second part is sort of more of a calculation of specific case. Right, so I guess this gives us an improvement of export and commit, which the way we defined it in the lecture was dependent on the time horizon, and then you can use this. It's sometimes called a doubling trick because we're like running the algorithm for like double the amount of time each time. Doubling trick. And it's a pretty general trick. Like the fact that we're doubling here, it actually like it works well for the square root of t. If you had a different shape of an upper bound, usually choosing a different shape of the or different amounts of times to run them works well. Yeah, and then I guess the other shortcoming of the export and commit was that it was dependent on the suboptimality gap, and then one of the homework exercises for the upcoming homework is going to be to show that we can also get rid of that assumption at the expense of a worse regret bound, which instead of square root of t, it's going to be t to the 2/3 for the total regret. Okay. Any questions about this homework or anything in general?
I have a question about the final proposition in the lecture notes, which is like how to parse the statement. So I already briefly asked in the Discord, but I'm still not 100% sure. Like, where do I put the exists and the for alls and?
Right. Yeah, I guess there's like a kind of just a draft of a claim, but so there, I guess we were just talking about why POM DPs are hard.
Yep.
And then the claim is, I guess there was one claim about the control problem being piecewise hard. And then you're asking about the second one, which is that I guess what I was trying to say there is the regret is can be exponential in the number of states.
So is that saying, so for any policy, I can find a POM DP where that policy is so bad that on average, it's just constantly making mistakes. And the cost
Right,
of those
so-
mistakes is exponential in the.
Yeah, so I guess maybe one claim to make is, yeah, okay, so I was actually very sloppy with what I wrote. But one thing you can say is that the total regret, yeah, the total regret, I should have written total regret there, I think, for any policy pi, oh yeah, for for all pi, we can find an environment. And it's fair to say. Right, thanks, Mitesh. So it's like on the order of the number of actions to the number of states. Okay, let me think if this is actually true. Maybe it's actually helpful to talk about a kind of example, because I think that's maybe more insightful. So basically, if you have a POM-DP, we can take, let's say, we just have a single observation, so we actually don't see at all what's happening in the POM-DP. Then we can define a POM-DP which is like this. That so take a word of length n of actions. So this is kind of like a password. And then the way the POM-DP is defined is that if you guess the first character of the password, you get to move on to the next state. Maybe I should say. Yeah. And then if you get the second one, you get to go to the next one. And so on. And then you get to a state which actually has a reward only if you enter the full password correctly. So the rewards are going to be 0 for all the states, except the last one is 1. And then let's say anytime that you enter something that's incorrect, then you just go back to the beginning. So this is for any a not equal to W1. Same for a not equal to W2. So we have this reset. And then let's say your hypothesis class is all of these for every password. So here, a policy that figures out the password for all of these has to try basically every password. So that's why it's the regret for any policy. Yeah, okay, so I guess what I meant here is the regret for the maybe I should say this the supremum over this hypothesis class of the regret is something that's on the order of the number of passwords here. And then maybe this is a meaningful statement now.
So it's kind of saying the amount of time you need to discover the optimal actions is exponential in the number of states.
Right. And then, yeah, I guess so this is not quite a regret band. Like it doesn't say anything about the time. So it's still like learnable because once you figure out the password, assuming the rewards are observed, so you get 1 reward, and then from then on you know the password and you can keep entering it. So you take this exponentially many steps to figure out the password, but from then on you figured it out. So it's still learnable. That's why I didn't say anything about like the time dependence, because it's not in that way. It's kind of a constant. The total regret is constant. It doesn't depend on the time. Or I guess I said like for t large enough. But so it's not quite the kind of how fast you're learning, or yeah. It was more to just say that the learning is hard as a function of the number of states rather than saying something about the rate at which the regret changes as time goes on.
Okay, and so it's really important that you're using total regret here. You're not saying anything about average.
Yeah, I mean, if it was average, we could put like a 1/t here. So it would be like kind of a fast learning in terms of the time in principle, because once you figure out a password, you can keep doing the same thing.
Yeah, but then the statement for t large enough stops making sense if you divide by t, right?
Well, I guess it still makes sense. It just says that the coefficient of the 1/t is big in terms of the number of states.
Oh, I see. Right. Okay, thanks. Hey, that was helpful.
Yeah, sorry, I was kind of sloppy, but I guess the spirit of it is just maybe captured by this construction with entering the password. Just because this is in contrast with the for MDPs, we had a bound. I think we had an upper bound of which was something like the number of states times the diameter of the MDP, and then maybe square root of the number of actions times, I guess, for the total regret. So the square root of t over. Maybe it's times the constant. We had some band like this for MDP. So here the regret is bounded linearly by the number of states. So the emphasis here was that for POMDPs, we cannot expect that it's going to be. We cannot even expect a polynomial time when the number of states is going to be exponential in general. So yeah, I know it was a little confusing because so far we've been focusing on the time dependence, but for this specific example, we're focusing on the dependence on the size of the. And this is also the diameter, by the way, because the diameter of this password POMDPs is the same as the number of states roughly. Hopefully that clarifies that a little bit. And I tried to fix the statement in the notes to say something a little more meaningful. All right. I guess we're at time, so feel free to go. And if there are other questions, we can stick around for a bit to talk about them.
Is it possible to ask a question about the new homework?
Sure. I'll try to give no spoilers, but.
I just started thinking about question 1, and I seem a little stuck on how do I should not depend on delta eta at all. Like my choice of m should not depend on delta eta.
Right. So we're trying to find an exploration time which works pretty well, reasonably well for any suboptimality gap.
I haven't started thinking about it, but would it be a matter of just trying to reverse engineer the maths, or is there actually some intuitive way to think about it?
Okay, I guess maybe like a hint to get started. I actually don't remember what this was, but we showed we proved the general kind of regret bound for etc m before choosing m for eta, which was we showed that this is something like lesser or equal than like m times delta times e to the minus whatever this was. See,
Something like delta squared over
delta squared over 4m maybe
4t.
4t. There's no m here.
I think the
Or,
maybe the
no,
one-
it is m, right? Because it's the number of times you will end the expiration phase. So anyway, so we had some factor like this for oh, it's actually sorry because this is the like t minus ma. So this is the probability that we picked a wrong arm,
yeah.
and then there was another term which was just something like this.
Yeah.
Because this is the regret we get from the expiration phase, and this is the regret we get from the exploitation phase, and within that, this was a bound on the probability that we picked the wrong arm. So and then we can look at this product here, right? Delta times e to the minus delta squared over 4m. So here, if delta is very big, then this exponent is going to be small, and if delta is very small, then the exponent is big, but you multiply by delta, so that part is small. So maybe one thing to do is to try to find a bound on this product in terms of m, which is independent of delta. That would be maybe a hint on how to get started.
Okay. Thanks for the help.
Any other questions? All right, then maybe we could stop here for today. Thanks everyone for presenting your solutions during the discussion. And,
Thank
see you
you.
next week.
See you next week. Bye.
Bye.
See you.
Bye bye.
Thank you. Bye bye.